So even today, I will show you how we can change the past.
Something like a time machine to go there and change it? Or?
Yeah, not literally like time travel, but something like that in the context of data structures. So in the we have to do a disclaimer. This is not really time traveling back, but in the context of data structures, we can actually do that. So before we even talk about this, from the title of the video, you can see that our talk will be based on this paper, Retroactive Data Structures, from Erik Demaine. You know Erik Demaine, he's the guy with the long hair that does advanced data structures on MIT OpenCourseware. If you know he's really cool guy. He explained there how these retroactive data structures work. But we will do something simpler. Some way we'll do it a little bit better, because we will even show you implementation of a retroactive data structure. So one step further. But before we even explain what are retroactive data structures, I want to, so for the viewers, and so if the viewers want to brag about knowing these retroactive data structures to their friends at the library or the pub, right? If they talk about data structures there.
Now, this may be the rum talking, but as long as the unpinning rate of the vortices is kept within 1.1 and 1.3, the Magnus force issue should be negligible.
Even drunk, he's still smarter than all of us.
Because who doesn't talk about data structures?
Who doesn't talk about data structures at the pub, right? So if they want to brag, I will give you an analogy, a real-world analogy between what are persistent data structures and what are retroactive data structures. So let's assume that this here is a point at the present. So this is present. There's some event that has happened in the past. So this is some event. And this is the beginning of the past. As we know, this is like somewhere 13.8 billion years ago, right? We have to take an event that has actually happened in the past. And let's say that this event here, we will take a common event between us two, and this is a very interesting event for me. I'm very grateful for this event, and that's you talking about Maribor with me. So when you mentioned Maribor first time, I don't know if you remember that.
I remember. Of course I remember.
So this is a very, very important event for me. But so we'll do something with it, right? So a persistent data structure, so I will here say Maribor, this is some event, and here's the beginning of time, the Big Bang. But what persistent data structures allows us is to go back in time before some event, and what we can say is, okay, let's not have this event. Let's assume that this event has never, so we go back in time, but you don't write to me about so you don't do this. So here, a persistent data structure will create another branch of the universe, of the world, of the data state, right? And let's say that this branch doesn't contain this event. But let's say we want to test what would have happened if this event did not happen. What would have happened after 3.5 years, so at the present time? And in order to do that, we have to relive the whole 3.5 years until we come to the present time. This is 3 years. But this is very slow. This is computationally very slow because we have to relive all of these 3 years. We may want to just skip them because reliving this takes time, right? So this is the persistent way of doing stuff. We roll back somewhere. We can roll back at time very quickly here, very, very quickly. But in order to go forwards, we have to relive all of the 3 years. So, but there's another way of doing this, and what is the retroactive version of this, right? So we have again present. You have again Maribor, some event. But now, what if I don't want to relive all of the years, but instead I want to just skip this event? delete this event from the timeline, and overwrite everything here.
So you don't text me back.
yeah, so I don't text you back. So I don't text you back, and now this event did not happen, right? But we want to overwrite, and now we immediately change the present here. So this is, instead of saying what would have happened if this event did not happen, but branching out, this is what would have happened if this event did not happen, but we change the present itself. We cannot have two timelines. This is the persistent data structure, and this is the retroactive data structure. But another idea is we can add even event. So we can have in both of the cases we can have an event here, but we can have the timeline here again, present, variable. But what would happen if I add here an event? So in a retroactive data structure, I will just add it here, and I want to say what has changed in the present if I have added this event. But there's another idea, is that this is called a partially retroactive data structure, because we're only interested at the present, what has changed in the present. So notice that we're not interested at how it got to the present. We're interested at what it changed in the present. But there's another idea. Another idea is we add, let's say again, we add an event here, but I want to query sometime in the past as well. So not only that I'm interested in the present, I'm interested as well in the past after changing an event. So this is equivalent to saying what would have happened some time ago, let's say a year ago, if 3 years ago we did not have this conversation. So where would have I been a year ago if 3 years ago we did not have this conversation? This is called a fully retroactive data structure, and this is the most difficult retroactive data structure, the most difficult data structure of them all. You can change the past, but you can also query the past. Okay, so we have this way of, you can tell this analogy to anyone at the bar and will understand it, right? We haven't talked about data structure at all. We have talked about the universe itself. The universe can be thought of as a huge data structure, right? But we'll see that in this paper they prove that there's no general way of taking some data structure and making it fully retroactive without. So there's no general way of doing this. So sometimes it will cost you a lot, and it is, in the worst case scenario, sometimes the persistent data structure. Okay, so we have this idea of what is a persistent, what is a retroactive data structure. But in order to understand, this is the paper itself, this talks about different data structures, different types of, how we can convert some types of known data structures to make them retroactive. But in order to understand retroactivity, we have to do an example. And an example, I have already prepared some cards, and I don't know if you can guess, but these are initials of, can you guess of which of them? Like what are these initials? You are watching this show right now. You want to guess?
I'm not sure what these.
So the initials Sheldon, Amy, Penny, Leonard,
I see.
Bernadette,
I'm watching
Raj.
Yeah.
The Big Bang Theory. They talk about time traveling a lot.
Yeah.
And there is a quote. There is a interesting quote that Sheldon says, and I love this quote. It says, chaos theory suggests that in a even deterministic system, if the equations describing its behavior are non-linear, a small change in the initial conditions can cause cataclysmic and unpredictable results. So we know that, we all can understand that. But and this is the way things here work. A small change here would cause huge changes could cause huge changes at the present, because the system is governed by nonlinear equations. But we in the data structure world, we constrain ourselves. So a data structure is just an abstract concept that we employ upon some given data, that we constrain the input and output of this data, so the management of this data. And the most basic, one of the most basic data structures we can have is a queue. So let us imagine that we have a queue. Let's imagine that this is a theater, and there's like Star Wars, and this is the line that the queue of the theater. And I have prepared these cards, and first will Sheldon come along in the queue, and at 1 minute, he will denote 1 minute here, Sheldon comes. Okay. Then Amy comes at minute 2. Amy comes at the queue. Then minute 3, Penny comes along.
Ooh, Penny and Star Wars.
Yeah, it doesn't match well, but at minute 4, we now dequeue. So this represents queue, so we put something in the queue. But at minute 4, we now dequeue Sheldon. So Sheldon goes in and watches, and goes in and sits down on his chair. So now the queue looks like this. Now it's Amy and Penny. Now Leonard comes along. He just logged the car. Now there's some gap, and at minute 8 is Amy let in. So DQ Amy. Now the queue is like this. Okay. So at minute 9, Howard comes along. At minute 10, Bernadette comes along. At minute 11, DQ. So the first person is Penny right now and goes into the theater, right? So so you can see that this data structure is just an ordinary queue. We don't have anything here, just an ordinary queue, but we keep track of what has happened. At minute 12, Leonard is let in. At minute 13, Howard is let in, so Bernadette is alone. Rush now comes along. And now at minute 15 and at minute 16, they're both let in. So now the queue is empty. They're all in the theater. Now we have a description of what has happened in the past by minute-on-minute basis. Like, what will happen if we change something in the past? Let's say that at time 3, Penny did not come. Let's say at time 3, Penny did not come. Now, if Penny did not come, of course, to make it consistent, we cannot have more DQs than what we have Qs, because there's no people to DQ, so we need to take away one DQ. But let's say that I want to ask you, what was the first person in the queue at between time 9 and between time 10? Can you quickly say what is the first person? Between time 9 and between time 10, there was some state in the queue. We don't know. We now have only this information to go for. We have to really quickly say what the queue looked like at this time, because we changed something here. If we're looking at time 9.5, let's say, the first person in the queue, it was Leonard. How do I know that at time 9.5 the first person was Leonard? Have to do one more observation. But before we do it, observation, we can also say that instead of taking away a query, we can also add a query somewhere. So we can also add a query. I don't have prepared queries to add somewhere, but we can add them later. The main observation, if we go back to the board like that, it was the first what we did in the first time without changing the past. If we observe something, is that we can order the queries in such a way that these queries here are one table and these queries are another table. And can you see why we can do that? So if I order them like this, these queries are independent of each other. So what I want to say here is essentially that if I go in time 3, I have had these in the queue, right? At time 4, I have DQ'd someone. But the DQ'd someone will be the first guy here.
Sure. Yeah.
So this will be DQ'd. Then time 8, a second guy will be so Amy will be DQ'd. Then at time 11, Penny will be DQ'd. At time 12, Leonard. At time 30, so they're independent of each other. So if I change something here, let's say that I swap their places. Let's say that I make it such that, let's say that this is P and this is L. No, I made the same card. Okay, let's say we have these two cards. If I swap their places here in the queue, so that Penny was that Leonard was first, and then it was Penny in the queue. So we had Sheldon, we had Amy. Instead of Penny comes first, we come with Leonard, and then Penny. So in this scenario, if we simulate the structure again, it will be Sheldon comes, Amy comes, Leonard comes now, right? Then we DQ Sheldon. Remember that this is at time 4. Then we say we queue Penny. So we swap these two places, but this is independent of these queries, because these queries anyone can be at the first place and taken away. So this is independent of how we. So both queries are independent as long as they're sorted. And if you want to find out who has been the first person at some time, it's pretty easy what you do. It's incredibly easy. So let's say at time 9.5, at time 9.5, what was the first person that has come? Well, that is in the queue, not that has come. So if I simulate this, I have to go to time 9.5 and I do these all operations from the start or from the end, roll back them. But I want to do it very quickly, and how I can do it very quickly is saying the following. At time 9.5, how many DQs have I seen?
2, right?
2 DQs, right? So at time 9.5, 2 people of this is taken away. So the queue at time 9.5 looked Leonard, Penny, Howard, because here this has not yet happened. These. So we know exactly how the queue looked at this time, because we can really easily say how many queries we have taken away, how many persons we have taken away, by just taking a look at how many queries are in front of this time. So have happened before. And how to achieve this is through something called an order-statistic tree. We introduce another data structure here, because even though this is a very simple queue, we know that operations of queue take constant time, right? But in order to have a fully retroactive queue where we can change the past and we can play around with these times and still be able to pinpoint who has been there, we have to introduce something called an order-statistic tree. And an order-statistic tree, for those in competitive programming, they already know, have implemented this probably. It's an extension to the balanced binary search tree. So it's just a balanced binary search tree. But it has two more operations. So we know in balanced binary search tree we can do searches, we can do inserts, and we can do deletions of keys, right? In sorted order. So we have sorted order, and we can insert something, we can delete something. So each of these here queues, we can imagine them as a leaves in our tree, or as a nodes in our tree, and we can remove a DQ operation, or we can insert some DQ operations. So we can say, okay, these DQ operations have never happened, so we remove them out of the tree. But in order-statistic trees, what we have two more operations. We have operation, if I give you time, so some time, 11, tell me in what index is this sorted in? So what is the index of this? So it's 0, 1, and 2, right? Time 11 has index 2 here. And one more operation is what time we have on some index, what operation we have on some index. So let's say index 5, we have this DQ13 operation. So why do we need this is the following. If I have this here sorted like this, so we have sorted by time. We have two order statistic trees. One order statistic tree is this, one order statistic tree is this. If I want to know at time 9.5, we take a look at this tree and we say, okay, what is the lower bound of 9.5? This is the first element that is equal or greater to 9.5. So this is the element. What is his index? It's 2, right? So 2 elements are in front of him. This is in logarithmic time in order statistic trees. So we know that 2 elements. We don't care what elements are in front of him. We know just that there are 2 DQ queries in front of 9.5. So if there are 2 DQ queries in front of 9.5, we go there, we go here, and we say what is on index 2 essentially here, right? So if these 2 queries reject these 2 Q operations, these 2 DQ operations reject these Q operations. And essentially our queue looks like this. So we can find the first element or the second or the kth element here in the queue. As long as we don't go over the time that we are in. So we set 9.5, we're at time 9.5. This has not happened here. So one thing to pay attention is the consistency problem. The consistency, that's why we can't do retroactivity in the universe, right? Because if we break something here, it won't be consistent at the present. So if you did not write to me about Maribor, then there won't be a consistency in the present, everything will change. And here's the same with the Q. If we take away some Q operations here, we also have to take away some DQ operations in order to have the same amount of Q and less or the same amount of DQ operations. Because if we have more DQ, we can't take people out of the queue if there are no people inside to the queue, right? This is the consistency problem essentially. And that's pretty much it for retroactive data structures. You can play around with the past and see how it affects the present, right?
I wonder if there's any data structure for the future as well.
That's an excellent question. I love that question. So we don't know what the future will hold, but that's why we do pre-computations. So in order to save time and to make our lives easier, we pre-compute something. And this is in the sense of the universe as well. If you want to make your life easier, you think, or you sometimes overthink. You try different scenarios. What will happen, right? If something or if something. And essentially, this is our pre-computation for the future. This is making our lives easier by trying out different scenarios in our mind for the future. An excellent question. This is a great philosophical question.
So for the past we have algorithms, for the future we have responsibility.
Exactly.